Hello, our Stat 512 final project was doing a regression analysis on ejection fraction using clinical predictors, specifically those uh, caught using blood work. So to start us off, we need to explain what ejection fraction is and why it matters. Ejection fraction is a measure of how much blood someone's heart pumps with each beat. It's generally used as a proxy for heart health and proximity to heart failure. So we can see here that ejection fraction percentages of less than 40% are indicative of heart failure. Between 40 to 55% indicative of low heart function. 55 to 70% is considered normal, and 70% is considered like a high functioning or exceptionally healthy. Low ejection fractions are generally considered one of the most foremost signs of heart failure, and early detection of heart failure can be critical for patient quality of life, patient survival. Um, Generally, it also can correspond with how invasive an intervention has to be. For example, catching heart failure early might not require heart transplant, whereas late detection can result in immediate heart transplant. So, how can we detect low ejection fractions early? So, to understand kind of our thought process, we need to first understand that using data collected during blood draws can be a good indicator for heart issues because heart issues those issues will show up in the bloodstream. Blood draws are already very common as part of many patients' physicals. These blood draws check a wide variety of things, including liver function, kidney function, blood sugar levels, fluid balance, and electrolyte balance, all of which can be thrown off due to heart failure. There's some prior literature that use biostatistics to suggest that certain measurements in a patient's bloodstream may be indicative of death from heart failure. These were generally noted to be serum fraction and ejection fraction, and so therefore we think it may be possible to kind of reconfigure some stuff and see that how data collected during routine blood work can be used to predict uh, what a patient's potential ejection fraction may be. The reason that this is unique is because would be done far quicker because it's just simply plugging in numbers and seeing what the predicted output is, and because people tend to get their blood drawn a lot more frequently than they go to a cardiologist, this could enable earlier detection. It would also be a cheaper method of doing like initial screening because initial screening is typically done with an ultrasound, which can be very cost intensive and time intensive.
Thank you, Sai. My name is Jake, and I will be looking at the data pre-processing and more so the overview of the data set itself before we really get into the regressionary analysis we did for our model. So, as Sai just mentioned, we knew we wanted to use ejection fraction as our main response variable, but we only got to using that after finding a suitable dataset itself. We first looked at Kaggle and other dataset collection websites, and eventually found one from a UC Irvine study, which was made by David Chico and Giuseppe German in 2020. Now, the dataset is labeled Heart Failure Clinical Records and contains 299 patients who had heart failure collected during their follow-up period, where each patient profile has 13 clinical features. This dataset, as mentioned, is directly from the study from Chico and German, which is called Machine Learning Can Predict Survival of Patients with Heart Failure from Serum Creatinine and Ejection Fraction. Now, this dataset was really crucial to us as it contained several predictors, I believe up to 12 that we could have used, and several also responses. To get into the follow-up study more so itself, this study that used the same dataset found that serum creatinine and ejection fraction were the primary two predictors that could be used to find heart failure in patients. This was a prediction model where they mainly use these in a format of logistic regression, where, again, these two predictors were the main ones they found that could predict heart failure. we didn't want to do the same exact thing as this study because we knew that we wanted to do something more unknown and, not just directly laid out by other researchers before us. So we decided that we could use ejection fraction itself as what we were trying to predict in our patients from the other predictors you may kind of already see here in this picture. So to explain the data itself, the data had all of these following variables that you can see on the right in this image. Now, I kind of circled this specifically, but ejection fraction, again, this is the response variable we will use for our study. It is a continuous variable, and we made sure that we wanted to look at this specifically since it would be pretty easy to tell whether the response would make sense or not, and it also was interesting seeing how, as I mentioned earlier, ejection fraction is something that can really predict heart failure or not in a patient. And as you can maybe see at the far right column, there were no missing values for any of the data's rows or columns, which was really phenomenal because this meant that we really didn't have to do any data cleaning or filling any entries or getting rid of any extreme outliers itself, which sped up the process a lot and let us more so look at the initial data analysis to begin with. So out of all of these predictors and variables we saw in the last slide, we really landed on 6 here that we wanted to use for our model. We figured that these ones were more so maybe relevant and easier to grasp and understand, but these were also the ones that we landed upon for our research question itself. The research questions can be seen more so independently in our study itself, and in our individual responses you will see the specific ones that we all chose. As mentioned earlier, ejection fraction was our main response variable, and this is the fraction of blood leaving the heart in percentage, importantly. As for our predictors itself, we had serum sodium, which was the level of serum sodium in the blood in MEQ per liter, then serum creatinine, which is the level of serum creatinine in the blood for milligrams per DL, then creatine phosphokinase, which is the level of creatine phosphokinase enzyme in the blood, mcg per liter, and then age, which was in year, and then high blood pressure, which was a categorical binary variable that takes the value of 1 if a patient has hypertension and 0 otherwise. We really wanted to look at high blood pressure as a categorical binary itself because we felt that this one was actually very significant in determining some differences between potential patients, and we really wanted to see the interaction of this high blood pressure binary variable with some other variables in our model, which you will eventually see as we get further into our presentation.
Now let's get into the mechanics of our study. To begin our analysis, we constructed a multiple linear regression model and aimed at predicting ejection fraction using predictors commonly found in our patients' routine clinical records. Our starting point was the initial equation shown below. We included an interaction term between high blood pressure and serum sodium because we suspected that hypertension might fundamentally change how sodium levels associate with cardiac output. To guide our analysis, we set out to answer the 5 following questions that represent the core of our investigation. Firstly, is serum sodium significantly associated with ejection fraction, and if so, what is the magnitude and direction of this association on a log scale? Second, does the association between serum sodium and ejection fraction differ between patients with and without high blood pressure, and if so, in what direction? Third, is creatine phosphokinase, or CPK, significantly associated with ejection fraction after controlling for our other variables, and how does effect size compare to the other lab markers? Fourth, is age significantly associated with ejection fraction after controlling for these clinical variables, and does it align with the expected pattern of age-related cardiac decline? And fifth, is serum creatine significantly associated with ejection fraction, and what does its effect size suggest about kidney function as a meaningful correlate of function in this group? These questions set the stage for our analysis, but as we quickly found out, the raw data required a bit more work before we could get a clear answer. Before we could trust any of our results, we had to perform our MLR assumption checks. As any of us who spend time working with real-world datasets know, the data rarely behaves perfectly on the first pass. If you look at the test results on the left, our Durbin-Watson test came back clean with a p-value of 0.6835, meaning we didn't have to worry about the significant autocorrelation. The Bruch-Pagan test returned a p-value of 0.1732, so our variance was relatively constant across the model. However, the Shapiro-Wilk test was our first major hurdle. It returned an extremely small p-value of 0.00002, which is a clear sign that our normality assumption was violated. You can see this visually in our normal QQ plot on the right. Those sample points curving away from the dashed line at both ends confirm heavy tails, showing that our residuals were not normally distributed. Beyond normality, we also noticed a massive red flag regarding multicollinearity. If you look at the bottom table, the values for high blood pressure and our interaction term were both above 1042. This indicated that our initial model was too unstable for reliable inference and required remediation through a log transformation, which we'll discuss in the next section.
Hey, I'm Jinwook, and I also go by Alex, and I'll focus on our model selection process and final regression model. After fitting the full regression model, we wanted to determine whether a simpler model could perform just as well. Adding more predictors does not always improve a model, so we compared different subsets of variables. To evaluate this, we used several model selection criteria using adjusted R-squared, Mallow-CP, AIC, SVC, or BIC, and PREST. These measures help us balance model fit with model simplicity. From this process, 3 candidate models stood out. The first model included only serum sodium. The second model included high blood pressure, serum sodium, and age, along with the interaction between high blood pressure and serum sodium. The third and most complex model added serum creatine, creatine phosphokinase, and we then added 10-fold cross-validation to compare predictive performance. This method repeatedly trains the model on part of the data and tests it on the remaining data. We compared the models using RMSE, where lower values indicate better prediction accuracy. The results show that all 3 models had very similar RMSE values, meaning the more complex models did not meaningfully outperform the simpler ones. And because predictive performance was nearly identical, we selected the most parsimonious model, meaning the simplest model and that still performs well. Our final model used only serum sodium. Since the response was log transformed ejection fraction, the coefficient means that for every 1 unit increase in the serum sodium, the expected ejection fraction increases by approximately 1.4% on average. The model was statistically significant overall, with a p-value of 0.0006, and serum sodium was also individually significant. However, the adjusted R-squared was only 0.0362, meaning the serum sodium explains only about 3.6% of the variation in the ejection fraction. So while the relationship is statistically significant, serum sodium alone is not a strong predictor of heart function. This makes clinical sense because ejection fraction is also influenced by factors such as heart muscle strength, preload, afterload, and structural heart conditions, which are not captured through routine blood tests. In conclusion, serum sodium was the only predictor that remained significant, and although predictive power was limited, it may still be a useful clinical indicator of cardiac health.
This is Chad. After addressing the normality issues within the initial model and making sure that the current model now matches all the assumptions of MLR, we moved on to criteria evaluation and cross-validation. For parsimony and inference, several criteria were considered and evaluated to suggest the best subset of variables present within the final model. It is worth noting that each of these criteria perform differently and prioritize different things, such as prediction, inference, simplicity, so on and so forth, which leads to different candidate models. The criteria that were considered are R-squared, adjusted R-squared, Mallow-CP criterion, AIC, SBC, and PRESS. Now, after the candidate models were identified, tenfold cross-validation was conducted in order to evaluate discrepancies within performance, mainly predictive performance. This was done by comparing the root mean square error, or RMSE, for all the candidates, which in turn would identify the gaps in predictive power of different subsets of predictors. Now, using the criteria mentioned beforehand, we narrowed down the candidate models down to 3 subsets of predictors. The first one only includes serum sodium, and this was suggested by AIC, BIC, and PRESS. A second included high blood pressure, serum sodium, age, and of course the interaction between high blood pressure and serum sodium. This model was suggested only by adjusted R-squared. And lastly, the model, which is the full model, retaining all predictors, including high blood pressure, serum sodium, serum creatinine, creatinine phosphokinase, age, and of course, again, the high blood pressure, serum sodium interaction. This full model was suggested by R-squared and Mallow-CP criterion. So, after the 3 candidate models were selected and identified, we used tenfold cross-validation in order to compare the root mean square error values across the 3 models in order to, again, identify the discrepancies within predictive power. Now, as seen on the picture to the left, all 3 models performed almost the same in terms of RMSE, with near identical values. Now, this indicates that there is little to no difference between the predictive power of the 3 subsets considered. That is why, for the sake of parsimony and for the sake of interpretability, the simplest model was chosen. With that being said, the current final model at this point was the log-transformed ejection fraction variable regressed on serum sodium alone. So now the picture to the left shows the summary of the final model selected, and the equation of the final fitted model would be log ejection fraction is equal to 1.635 plus 0.014 multiplied by the serum sodium levels. It is worth noting that both the intercept and the coefficient of serum sodium are significant in this case, and since ejection fraction, which is the response, is on the log scale, the inference here is that every 1 unit increase in serum sodium is associated with around 1.4% increase in ejection fraction, holding all other variables constant. This is the main takeaway in terms of clinical context here. So, based on the model summary from the previous slide, the model was statistically significant overall, with an F statistic of 12.19 and a p-value of 0.0006. And of course, as mentioned beforehand, the intercept and the coefficient of serum sodium are both significant, with p-values of 0.004 and 0.0006, respectively. Now, despite the statistical significance, the model's explanatory power is very limited. This can be seen through the adjusted R-squared, which takes a value of 0.0362. In context, this means that serum sodium only accounts for 3.6% variation in log ejection fraction, which, clinically speaking, would mean that serum sodium doesn't account for a lot of variation within ejection fraction in general. However, we do have very small p-values, which means that the most parsimonious model that we reached at the very end, retaining only one predictor, serum sodium, still serves its inferential purpose, and this, in context, would indicate that there is, in fact, a real association between serum sodium and ejection fraction, despite there not being strong explanatory power.
To wrap things up, these are the final takeaways from our project. Ultimately, serum sodium was the only predictor that remained statistically significant across all versions of our model. Now we have to address the fact that our final R squared was quite low. But as a team, we don't see this as a failure of the model. It's an actual reflection of the biological reality. Ejection fraction is actually primarily governed by mechanical forces like preload, afterload, and contractility, factors that routine blood work markers aren't designed to capture. You're measuring downstream chemical indicators rather than the upstream mechanical causes. So limited predictive power was exactly what we anticipated. One of our most notable findings was involving age. While it's common to think that heart function slows down as we age, our models showed that ejection fraction doesn't follow this same pattern as heart rate. This finding is consistent with NIH literature and serves as a reminder that cardiac efficiency is more complex than just the number of years a patient has lived. In conclusion, while blood work might not replace an ultrasound, serum sodium serves as a vital, easily accessible smoke signal that can help us monitor heart health more frequently and catch potential issues earlier.